All right, we're just going to write this repeated multiplication in exponential form. So we got two parts to it. Remember, we have the base, which is the number that's being repeatedly multiplied, and then you have the exponent, which is how many times it is being repeatedly multiplied. So on this one, we can see that the 8 is the number that's being repeatedly multiplied, but how many are there being multiplied? 1, 2, 3, 4, 5, 6, 7. So this ends up being 8 to the power of 7. That's how that reads, 8 to the power of 7. But it's written in a mathematical form, so we don't actually have to write that out completely in words. There's our objective for the day. I can simplify exponential expressions when bases are the same and are being either divided or multiplied. Take 30 seconds and copy that down, please. All right, so when the bases are the same, it'll create a unique rule for us. But if they're not the same and the bases are being multiplied or divided, then we can't exactly work directly with that stuff. The bases have to be the same before we can apply these rules. So just as a quick reminder, just like we saw in the bell work, the base, here the 5 would be called the base number, and the 4 is the exponent. The base is the number being repeatedly multiplied. The 4, the exponent, tells you how many times it's being repeatedly multiplied. And you'll see this, I believe, on the assignment as well. If you have just a number by itself, it's really a power of 1. So there's another application of what we see as a phantom 1. But if you need to see that, because I think it's going to help us while we're getting used to these rules, to see that exponent of 1, well, since we're dealing with exponents, if you can at least see that, then you know what you're working with. So it says simplify to a single power. Now on the assignment, what you're going to see is it's going to have 2 right here as your base, and then it's going to show a box right here. Okay, so all you have to do is fill in the box. Okay, but what number goes in the box? Because right here we got exponents of 2 and 4. The bases are the same, so this is one of those unique cases, and this is what happens to this. Okay, so let's start with first this 2 to the power of 2. All right, so that if I were to expand that, that would be 2 times 2. Now we're going to multiply this by the other exponent, 2 to the power of 4. So that would be 2 times 2 times 2 times 2, 4 2's being multiplied. But what you notice now is that we have complete multiplication, but all the bases are the same. So on this problem right here, I can see that the 2's are the bases. So I'm going to say I've got a 2 right here, and all I'm going to do at this point is just count how many there are, right? So 1, 2, 3, 4, 5, 6. So in the box, you'd put a 6 right there. Now, do you have to expand it? No, because we can apply the rule. How did we get 2 to the power of 6 without expanding it? Well, just look back here at the original exponents, 2 and 4. What did we do with those exponents? Well, what we did is we took the 2, the base, and then we took those 2 exponents, 2 and 4. And again, you could even think about this. What would you have to do with 2 and 4 to get a 6? You'd add them together. Okay, so this is our rule. When the bases are the same and you're multiplying them, just add the exponents. So there's the rule. This is more abstract. So it does work with letters as well, but for the most part, we're only going to be seeing numbers on this stuff, just like we did on that last problem. So once again, though, the idea here is you notice that when the bases are the same, if they're not the same, we cannot apply this rule. Yes, it's the product rule, not that I think anyone cares, but we're not ever going to quiz you on what the name of the rule is. So when the bases are the same and they're being multiplied, and that's the crucial part here, that's one of the 2 operations we're looking at in our objective. When we're multiplying those bases, take the 2 exponents and then add them together. It's possible, by the way, to have more than 1 exponent in there. So if for some reason you had another base x, maybe to the power of c, well, then you'd have c plus a plus b. And keep in mind, sometimes the exponents can be negative. While we may not understand what that means, then you may be adding negatives as well. So for this problem, once again, the first thing we would need to ask is, are the bases the same? Well, yes, they are. And since they are the same, base 5s, we know that we can add the two exponents, right? So this is 5, base 5. Then I have exponents of 7 and 6. So I'm going to take those two exponents, 7 and 6. Of course, you're always welcome to expand these, but I'm not going to do that because writing this out 7 and 6 times is just more work than I want to do. So in the exponents, though, we got 7 plus 6. When you add those together, you should get 13. And again, on the assignment, all you're really doing is filling in this box. Oh yeah, so this is the first time, yeah, we see 3 bases, and they all have exponents. So once again, we'll reduce this to one single power, but the base should be the same because these are all base 11s. Now once again, if it helps you to see, this 11 has an exponent of 1, then put it there. But you need to understand that there is an exponent there, and it is 1. Because if you don't, what you may end up doing is just adding 9 and 11 to get 20, and that's not going to be correct. Okay. So here, I can see that all my bases, base 11s, and these are all being multiplied. So since they are being multiplied, I'm going to take all 3 exponents. 1, and we had 9, and we got 11, and I'm going to add those together to create my new exponent. So this ends up being base 11 to the power of 1 plus 9 is 10, plus 11, and it's going to be 21. That's it right there. Of course, like I said, on the assignment, I'll just fill in the box for the 21. That may seem oversimplified, you guys, but that's really all this is if you see that the bases are being multiplied and they are the same, add the exponents. But I'll stress this again, if, let's say this base was not 11, then I could not combine it with these other base 11s. Okay, it has to be the same base. All right, so this is a new one. We got base X on this one. You guys try this one out, 15 seconds, then we'll go over it, okay? If you're still working on that, do finish. But I'm going to start here. I'll just show the expansion again just so you can see it. It's not ever a requirement that you do expand it for this particular assignment, but I'm going to just to show us what is happening, right? So I got x to the power 5, so that's 5 x's, 1, 2, 3, 4, 5 x's. And yeah, these are all being multiplied. And then we also got x to the power 4, all being multiplied, 1, 2, 3, 4. And in the beginning there, they were already being multiplied. So since the bases are all the same, they're base x's, I can take my base x and then just count how many there are. 1, 2, 3, 4, 5, 6, 7, 8, 9. Now this one wasn't too bad because there was only 9 x's right here. But when the bases become a lot bigger, then this becomes a little bit more impractical, okay? Could we have used the rule? Yeah, we could have. You could have said right here, you can see that the bases are the same, so you would have had base x, and then you would have taken the 2 exponents, 5 and 4. And since the bases are being multiplied, all you would need to have done is add those 2 together. The exponents are added. So you take the base x, 5 plus 4, that's 9. Same answer, slightly different method. So are you always welcome to expand these? Yes, you are, but it's never a requirement that you do. My recommendation is you get used to this rule because it is a nice shortcut. Okay, but it is the same answer either way. So yeah, on problems like this one, where the exponents are much larger, yeah, we would never expect you to actually expand these. But what we do want you to notice is that the bases are the same. That's the first thing we need to notice. These are Q's. And then what are my exponents? We got 31 and 18. So I'm going to take my base Q because they are the same, And with my exponents, 31 and 18, since the two bases are being multiplied, I will add the exponents. So I end up with q to the power of, looks like 49. Okay, so something like this, and do keep in mind for the assignment, it's possible you may have to type this in and not just enter the exponent. Okay, remember, of course, you type in the q first, and then to access the exponent function, you'll have to use Shift 6. Okay, and you'll notice just above the 6 is this little caret button. That's the exponent button. Okay, then you'll type in 49. Then you just push enter. So let's go and simplify this. And now it's division. So do understand that when we see the fraction line there, that this is division. But the other thing we need to notice on this is that the bases are the same. So there is a rule that we can apply, but let's look and see what actually happens with this. Okay, so what I mean by that is I'm going to expand these two. So I'm going to take 5 to the power of 4 here. And so I got 4 5s. 1, 2, 3, 4 5s. And these are all being multiplied. And then in the denominator, I got 5 to the power of 2. So that'd be 2 5s being multiplied. Now, if you go way back, not just, I think, the 7th grade, but also possibly 6th grade, you saw that you can simplify fractions like this with what was called prime factorization. Whether you remember that or not, doesn't really matter, because as long as we understand that anything divided by itself is 1, divide, oh, there we go. If we can just understand that, then we know where to go from here. Because right now I see right here, that's 5 divided by 5. Now I cross those out with a 1 so that we understand that that is actually a 1. Same with this other 5 divided by 5 right there, which is 1. Okay, so what would we be left with? Because at this point I could just say, well, like, you got these 2 1s. I'm just going to make them phantom 1s, though. So what do I got left over? Well, it's base 5. But how many 5s do I have multiplied here? 1, 2. So I end up with 5 to the power of 2 right here. Now, since this is new, we're kind of looking for a pattern or a rule to apply. And while 5 to the power of 2 does match the denominator here, that's not really what we're looking at. Okay? What happens with these 5s right here is that the bases are the same, right? And you take the exponent of the numerator and then the exponent of the denominator, and it has to be in this order. And what did we do? Well, you took this 5 and you pretty much took this other 5 away. Okay, so by take away, that would indicate that we are subtracting the exponents, which means that here, if you took 4 minus 2 there, that's how you get the new exponent of 2. Okay, so again, don't get this confused, because the denominator exponent matched 5 to the power of 2 with the answer. It's really that we were subtracting. And that subtraction comes from this idea that anything divided by itself is 1. Okay. So there's our rule. Again, any of these could be numbers. Bases could be numbers. They could be letters. And then the exponents are usually numbers. But this is the rule. When you divide bases that are the same, take the exponent of the numerator and subtract the exponent of the denominator. So that pretty much takes care of our both parts of the objective, as long as you can see that when you're dividing the same bases, you subtract exponents. And as long as you can see that when you're multiplying the same bases, that you add the exponents, then you have the objective down. So even on this one right here, we got base 8s, okay? So we know that the answer should also be base 8. But once again, it has to be in this order. You take the exponent of the numerator first. So in this case, it's 11. And then the exponent of the denominator, which is 6. And then you subtract those. Okay, so this is going to give us a more simplified exponent. 8 to the power of 11 minus 6, I get 5. 8 to the power of 5. Now, if by chance we needed to evaluate these, although I do not believe we have to on the assignment, we just type it into the calculator and be done. Because we definitely don't want to have to do 8 multiplied by itself 5 times. Not on paper, not in our head. The calculator will do that for us if it's necessary. All right, base 51s. Again, it doesn't matter what the base is when they are the same. As we see here, we'll keep the base the same. And then we'll just work with the exponents. Well, this one's division of the bases. So I'm going to take the 2 exponents first in the numerator, the 62 exponent there, and then, and it does need to be in that order, then the denominator exponent, which is 24. Yeah, I just need to subtract those. So this ends up being, well, it's the same base, 51, but now I got an exponent. 62 minus 24, so that'd be 38. So this is 51 to the power of 38. All right, so this one, yeah, we got some letters for our bases. Try this one out, 15 seconds, and we'll go over it together. All right, so for this one, bases do match their x's. So I'm going to keep my base x. I'm going to take the exponent of the numerator 7, and then the exponent of the denominator 2. And since the bases are being divided, I need to subtract the exponents. So I end up with x to the power of 7 minus 2, which is 5. X to the power 5, that would be our simplified form of the original expression. If you can just understand these 2 rules, the assignment's going to go pretty quick. So on this one right here, we can see we are dividing the 2 bases, base m's. And then again, it has to be in this order. I'm going to take the exponent of the numerator first, 21, and then the exponent of the denominator here, 37. And since we are dividing the bases, we need to subtract the exponents. But I think some of you guys noticed on this one that the exponent of the numerator is smaller than the exponent of the denominator. That's okay. It is possible to have more, to have a higher exponent in the denominator, okay? So what does this mean? It just means we're gonna have a negative exponent, and that's okay. So on this one, it looks like we get negative 16. Now what does this mean? We'll go over that later in a different lesson. But for now, that's as much as we need to see right there. There's our objective. So we can see the 2 rules. When we are dividing the same bases, we subtract the exponents. When we're multiplying the same bases, we add the exponents. And again, please do not overcomplicate that. It really is that simple if you can just get that down.